Lesson: Feature Selection and Engineering through AI. Feature selection and engineering are pivotal components of the data acquisition and pre-processing phase in artificial intelligence and machine learning projects. These processes significantly influence the effectiveness and efficiency of predictive models. By focusing on the most relevant features and transforming raw data into meaningful inputs, data scientists and AI professionals can enhance model performance, reduce computational costs, and improve interpretability. This lesson delves into the actionable strategies, practical tools, and frameworks that professionals can apply to optimize feature selection and engineering, thus enriching their proficiency in the CompTIA Data AI Certification context. Feature selection is the process of identifying the most relevant variables that contribute to the predictive power of a model. It reduces the dimensionality of data, which not only speeds up computation, but also helps in mitigating overfitting by eliminating noise and redundant information. A variety of techniques can be employed for feature selection, including filter, wrapper, and embedded methods. Filter methods, such as correlation coefficients and mutual information, evaluate the relevance of features based on their intrinsic properties. For instance, using Pearson's correlation coefficient, one can assess the linear relationship between each feature and the target variable to select the most correlated ones. Wrapper methods, like recursive feature elimination, involve training a model on different subsets of data and selecting the subset that yields the best performance. These methods are computationally expensive, but often result in superior feature sets. For example, RFE can be implemented using Python's scikit-learn library, where features are recursively pruned based on their importance scores until the optimal set is achieved. Embedded methods integrate feature selection within the model training process, exemplified by Lasso, which penalizes the absolute size of coefficients, effectively shrinking some to zero, and thus performing feature selection. Feature engineering, on the other hand, involves creating new features or transforming existing ones to improve the model's predictive power. One common practice is to handle missing data, either by imputation with statistical measures such as mean or median, or by employing advanced techniques like k-nearest neighbors imputation. Scikit-learn provides an imputer class that facilitates these tasks efficiently. Moreover, categorical variables often require encoding transforming them into numerical values to be digestible by machine learning algorithms. Techniques such as one-hot encoding and label encoding are widely used, with libraries like Pandas offering straightforward implementation. Scaling and normalization of features are critical to ensure that all features contribute equally to the distance metrics in algorithms like k-nearest neighbors and support vector machines. Standardization rescales data to have a mean of 0 and a standard deviation of 1, while min-max scaling transforms data to a fixed range, typically 0 to 1. Scikit-learn's standard scaler and min-max scaler are practical tools for these transformations. Furthermore, polynomial feature generation can introduce nonlinear relationships between features, thus enhancing model complexity and capability. This can be implemented using Scikit-learn's polynomial features class, which generates new features by raising existing ones to a specified degree. Real-world challenges often necessitate custom feature engineering strategies. Consider a case study involving a retail company aiming to predict customer churn. The raw dataset might include variables such as purchase history, customer demographics, and interaction data. Feature engineering could involve creating new features like average purchase value, frequency of purchases, or recency of last purchase. These engineered features provide deeper insights into customer behavior, potentially leading to more accurate churn predictions. Furthermore, temporal features such as day of the week or month can be crucial in capturing seasonal patterns in customer activity. Incorporating domain knowledge is essential in identifying and creating such features that align with the business context. AI-driven tools and frameworks have emerged to automate and enhance feature selection and engineering processes. AutoML platforms, such as H2O.ai and Google's AutoML, leverage AI to automatically select and engineer features, reducing the manual effort required in traditional approaches. These platforms employ sophisticated algorithms that iteratively test different feature combinations and transformations, optimizing model performance. For instance, H2O's driverless AI uses advanced techniques like target encoding and feature clustering to generate high-quality feature sets automatically. Despite automation, human expertise remains invaluable, particularly in understanding the nuances of the data and ensuring that engineered features align with the problem context. Professionals must balance automated solutions with their domain knowledge to achieve optimal results. Moreover, ethical considerations must be accounted for in feature selection and engineering, particularly in ensuring that models do not propagate bias or discrimination. Techniques such as fairness-aware feature selection can mitigate these risks by identifying and excluding biased features. In conclusion, feature selection and engineering are integral to the success of AI models, directly impacting their accuracy, efficiency, and interpretability. By leveraging a combination of manual techniques and AI-driven tools, professionals can enhance their data preprocessing workflows, addressing real-world challenges with precision and insight. As AI continues to evolve, staying abreast of emerging tools and methodologies will be crucial for professionals seeking to excel in the CompTIA Data AI Certification and beyond.